In these types of questions, you have energy transfer through radiation. A lot of times the story will be about somebody being outside, and it'll tell you the skin emissivity because it's cold out or it's hot out, and basically heat is being lost through the skin or some other surface, and it's not being conducted through something, it's being just radiated away. It's not convection, it's not conduction, it's radiation. So in other words, it's just like, cold day, you're outside, you could almost feel the heat leaving your body, and in this case it's going to be through radiation. So what we need to do here again is list the variables. We have a student walking outside and it's cold out, and it tells you some information. So he's walking to the store and it takes 15 minutes to walk to the store. It tells you, so you're outside for a while, how much energy is lost during this time. Okay, so the first thing we're going to go for is our area. And the area is basically the area of the skin, the surface area. And that's given. We don't even have to worry about that. It's in meters squared. Everything should always be in meters, never centimeters. In this case, it's given. And then we have our emissivity, and that is just going to be the lowercase e. That's also given as 0.90. That's just how much energy is given off. It basically has to do with how much energy can be left or given off through the skin, how good the skin is at giving it off. So let me rewrite that a little bit more nicely. Then we have Stephan's constant, and I might be pronouncing that wrong, but this is how it looks to me. So that is this symbol here. It's a Greek letter, and it is a kind of a pain to write out, but it is what it is. It's very useful. 5.66696 times 10 to the negative 8. And the units for that aren't given here, but they are watts per meters squared per degrees Kelvin to the 4th. So again, I'm not sure why it's not given here, but it's just not. But I like units. Well, they're important because they represent real life. So now we need the outside temperature in Kelvin. So the outside temperature in Kelvin, which is the unit of measurement for temperature. And basically what we had to do, it tells us the outside temperature is 45 degrees Fahrenheit. But it also tells us the formula to find the temperature in Kelvin is this. So I'm just going to call it T outside. And what I'm going to do is just use that equation. So degrees Fahrenheit is what, 45 degrees F plus 460 times 5/9. And what we get when we do that is basically 280 we'll just go a little further here, and that's degrees Kelvin. So it has to be in Kelvin. In fact, I'm going to put just a big arrow. Kelvin. Well, degrees Kelvin. Now we need our skin temperature. Again, we need it in Kelvin. So I'll just do the same thing as before. Temperature of skin. And the temperature of the skin is 93.7 degrees Fahrenheit plus the 460 times the 5/9, and that will give us a skin temperature of 307.6 degrees Kelvin. Finally, what we need, and I didn't leave much room for it, is the change, the change in time, delta t, lowercase t, and it is given to us in minutes, and that's not good. Doesn't work because the units are needing to be in seconds. Everything should be in seconds, and so our delta t is going to be equal to these 15 minutes, and there is 1 second for every, there is 60 seconds for every 1 minute, And so the minutes will cancel out, and we end up with 900 seconds. Okay, so we need to identify the unknown values and the units of measurement. We want to find net energy transfer from the student's body. So the unknown values that we need to find are basically P net, which is the radiated energy. This is now radiated transfer, and that is measured in watts, which again is just joules per second, and that is going to help us find the actual energy transfer, which is Q. How much energy is lost? Transfer in joules. So what we're going to do, just to kind of give you an idea of what's going on, is we need to find how much energy is lost, because that's really it. That's the bottom line. That's when you're dealing with energy, how much is lost. And to get that, we need to find the rate at which energy is lost given this situation. And to do that, we need to find the rate at which energy is lost given this situation, and then basically take into account how long that the energy was being lost for, in this case 15 minutes. So the next step is to select the equations, and to find our rate, the P net is, and here's Stephan's constant times the area times the emissivity, and now this part is interesting here, times T2, the second temperature, to the fourth, minus the first temperature to the fourth. So not squared, but to the fourth. And the other equation that we will use is just the little old Q is equal to P delta T. Alright, hey, I spelled that right. Now we need to solve for P net. So this one is, involves a lot of numbers. And the first one is that Stephan's constant, which is 5.66696 times 10 to the negative 8. And the units for that, like I said earlier, is watts per meters squared. Kelvins to the fourth. Oh, there's that to the fourth. Now, take that, we multiply that by the area, and the area is 1.2 meters squared. And then we multiply that by the lowercase e, the emissivity, which is of the skin, 0.90. And then we multiply that by the difference of those temperatures fourthed. So I like to get positive numbers here. That should not be there, a little dot. Oops. So 307.6 degrees Kelvin to the fourth minus 280.6 degrees Kelvin to the fourth. Okay, and you got to be very careful how you plug it into your calculator here. Just follow the order of operations. Use parentheses whenever you're in doubt, and you'll be fine. But yes, you had to actually take this number. You have to use a little caret, so it'll be, in your calculator you'll have to go 307.6 caret 4 in order to calculate that out, and the same thing for the other one. So just be aware of that. And when you do that, you end up with the number 168.5 watts. That's the rate of which energy is transferred. How much joules per second? Okay, so a watt, don't forget, is, okay, so why watts? Because the meters squared cancels out here. The kelvins to the fourth cancels out when you do the subtraction there. You end up with watts. And don't forget, what is a watt? It's a joules per second. So in our next thing here, I'm going to actually set that up just like this. So Q is equal to P times T. So P is 168.5. And instead of putting watts, I'm going to put joules per second, because I want that to cancel out with the seconds here for the time, the change in time. And so it turns out that the actual amount of energy lost is a lot. And there it is.